I'm Peter Bindels. Welcome to a simple solution to a complicated problem. So the first question I have is, who are we making a simple solution for? We have build systems, we have complicated build systems, but who are we actually trying to target? Who is going to be using it? Is it going to be just this guy? He's made a complicated build system. Maybe he could use a simple one. Maybe we shouldn't just target him. But what about all the experts? Maybe we should just not be targeting just the experts of build systems, because they probably know how to use the complicated ones. So maybe everybody at the audience, at the conference. That's probably still too narrow. What about just everybody who knows how to use a language? Well, that might help, but it's still not wide enough. I mean, we're still excluding a whole bunch of people. A whole bunch of people that would like to use a build system and like to learn the language. Are we not including them yet? What about people who are new to this language? Like people who use Java. Or maybe anybody new to programming at all. So what about students? Just getting their first introduction to a computer at all? Or kids? What's to say that kids shouldn't be starting with C++? I mean, how far do we go? Well, maybe this is a bit too far. I don't think he can read yet. So maybe we should have somebody who can read and write. It would be nice if you understood the keywords, so you can read the language and understand that for loops mean that you're looping for some amount of time. And it would be nice if you have a computer. But having a recent one isn't necessary. Maybe a 10-year-old one should be fine. So I'm targeting something that's really simple to start. It shouldn't be hard to begin. And you should be able to take the things that you've learned and go way beyond. You should be able to take the easy solutions, use them to extend as far as they can go, and when you're done with what they can do, when you need to go beyond what they offer, you should have a very easy upgrade path. You should continue with the knowledge that you have and build upon it so you can keep learning. So in the end, this is all simplicity. And I know that pretty much everybody was at Kate's talk, so I'm not going to talk about all the simplicity. But there's one quote that she had that I really, really love, which is, "Is this really all I need to change?" And that's with respect to having some kind of good set of code, where this is the only change I need to make to get it to do something. I don't need to change build files. I don't need to change something across the entire code base. Think in CodeSmell's shotgun surgery. If you can make something simple, it's going to be good. So why are build systems more like this? This is not good. So let's talk about what a build system actually has. The total build system is built of a build system driver. It's the thing at the top, the thing that you call, the thing that starts everything, and preferably is one command, but maybe it's not. There's something that figures out what the dependencies are. It's probably you. There's something that figures out how to retrieve a package. That might be you. You can have package information that comes out of it that needs to go into the build system to create commands that then are run by a tool that runs the commands. So way before time began, we had a whole ton of manual labor. You type in a command to compile, you type in a command to link, you type in just all the commands. And with respect to package information, we don't have any package information. We just install everything globally on the system. Everybody has the same version, everybody uses the same thing. If you upgrade it, everything breaks. It's nice. But then we got to the point where you figure out that this is not working. I have 15 commands to type every time I compile. And if I forget one, I get a build that works but crashes. So let's put it in a shell script. And now I have everything in a shell script. I have a reliable build, sort of, but it's slow. At this point, it wasn't multi-core yet, but I'm recompiling everything every single time. There has to be a better way to do this. So somebody set out to make. And we get to the make era. And I've put package config in here. It's sort of in this time frame, and there is a little bit of that, but mostly it's still just global installs. And make was great with respect to the build system and with respect to comparing it to a shell script. But make has a problem. And this is probably the best way to represent it. This is an XKCD about standards. And it infers that there are more standards, the more that people think, this is terrible. We need to have a universal fix for this. But actually, this comic is not correct, because there are not 15 competing makes. There are at least 24. I've put them in alphabetical order so you can read it more easily. And you'll note there's 2 missing, because we have an alphabet with 26 letters. So there's A make and L make, which don't exist yet. But L make shouldn't be confused with I make, of course. Go Matt. But this isn't helping. This list is from 2011. So maybe at some point somebody made these already, and there's way more. But you know what? I have the solution. We can use Unicode. Smiley make. But make has flaws. Make is not great. And somebody went on and made a tool that has a better interface, which is CMake. Now this is arguable. Is it better? But CMake did offer a higher level of abstraction. It used make underneath, so everybody could use it. And it had package information, which means that you can finally find packages in a reliable way in your build system and use them, instead of relying on keeping your fingers crossed. And this works fine, but you'll notice that make used to do more. It used to also have the upper part. So we're using make in a degenerate kind of form. We're just using the bottom half. And if you're using half of a tool, it's going to be slow, because it's not meant to do just half of it. It's going to try to do everything else and then find there's nothing to do. So somebody picked that up and made a tool that replaces make, but only in this place. And that's Ninja. A Ninja replaces it, makes it way faster, so it's like a Ninja. And this makes it better. And this is basically the first beyond make point, where you don't need make anymore to build things. And then you can put things on top of this, because the top 3 boxes are still manual labor. And who's a fan of manual labor? Well, that's Arvid. So I'm one that doesn't like it. So I'd like to automate everything. So there's VC package on the top right. Maybe that's a good solution. There's Conan. There's a whole bunch of alternatives. On the top left, there's CPP dependencies, which I'll come back to later in the talk, which does the dependency derivation for yourself. And at the top, there's a shell script. Yes, we're back to shell scripts. And that tries to kick off everything, build everything, front to back. This actually works pretty well. But what if I didn't have to make a shell script and install 5 different tools to do this? We just have one tool. Well, this brings me back to the point about build systems and complexity. Because why do build systems always tend to complexity? It's not such a hard problem. You can build Hello World. Everybody knows hi. What makes build systems so hard? Okay, it's not aliens. It's corner cases. Because build systems handle so many corner cases. You wouldn't believe. They build object files, they pack static libraries, they build executables. If you feel adventurous, they build static libraries or shared libraries. They can run your unit tests, and they should. They can run a code formatter. They can run static code analysis. They can upload to your embedded target. They can send a binary to a binary package repository. They can do a whole ton of other things, especially running things in sudo. That's especially something that I've seen them do, and you really shouldn't. But this is not an exhaustive list. There's way more they can do. So this is one reason why they're complicated. And the second one is actually a new thing. We've got modules. We've almost got modules. So what are modules from a build system point of view? In a build system, you're trying to look at files as if they are files that you take, you transform them in a given way without having any kind of MP-complete problem in it to a output. So I take a source file, I compile it to an object file. I take the object file, link it to an executable. I take the executable, run it. These are all simple things. From a build system point of view, if I have modules, I need to read the source to figure out in what order to compile them in. Which means that my build system needs to become way more complicated to do that. And there's a whole lot of build systems out there, like Make, CMake, and others, that currently just cannot do this. Which means that either we don't have a build system that can build modules, or we don't get modules. And both of those are not good. And there's the third thing. Build systems have a lot of complexity because people try to put everything in the build system, and the worst one is generated code. So we have, say, protobuf. Protobuf compiles a proto file, it compiles it to a C++ source file. Then we take the C++ source file, compile it to an object file, take the object file, link it to an executable. Where does the protobuf compiler come from? Maybe we can just put that in the same build. And now we have a build that runs a compiler, links it to an executable, uses that executable to build source, compiles that, links it to an executable. I'm seeing a problem. Because you can also just depend on a generated source file from the protobuf compiler, recursively. If you look at that from a build system point of view, this is really hard to get right, and you really just shouldn't be doing this, but people do it anyway. So let's look at build systems in a different way. We can put them in 4 categories. We have the procedural ones, the simple ones, the shell script. We have the functional ones, which is make, and a different one I'll talk about in a second. There's declarative ones, and there's prescriptive ones. And I prefer the term generative because it's basically what you get if you prescribe something. So the procedural build system is a really simple one. It does your build steps in the order to run them. It doesn't reorder anything, it's not efficient, it's not optimal at all. It's reliable. It's easy. You understand what's going on, but you do need to understand that this is 100% manual. I have omissions, I have bugs, I make typos, I accidentally forgot to update it. I need to understand the entire compile process. I need to explain to somebody, starting with a shell script or with a build system, that they need a compiler, they need a linker, what all these things do together. So it's not a good fix, it's not a good solution. And it's very easy to mess up. If you accidentally forget to update the build system, or you make a typo, you forget a file, you forget to update a file, it breaks. So this is bad. And we shouldn't be making new procedural build systems. So let's go to the second category, functional. This is basically defining for the computer, for the build system, how to look at your source code or at variables, and how to make it figure out what things to build. And this is great if that's the kind of thing that you vary on. But how often do you vary on those things? It means I have a compiler, I have a linker. I maybe have a protobuf compiler or 3 other, and that's what this thing is good at varying in. And it can handle the incremental builds. It's better than a shell script. It can handle figuring out actual dependencies. It can handle dependency files being generated by your compiler to figure out which things should be rebuilt if you change a header file. That's good. It can be portable. It can be portable. It doesn't have to be. But they are really unpopular. How many people in here use make directly? I see like 5 hands, counting enthusiastically. They're really hard to diagnose and fix, and there's a lot of implementation incompatibility. So who here of the people that use make support more than 2 kinds of make? Giving you a bit of extra time? Nobody. We had 24. That's surprising. But let's have a small aside. Perhaps only move sideways. So I tried to fix make, because I tried to use make, and I figured out that actually it is really good if you use it for what it's meant to be. But there's a limit that I hit that I didn't like. I had a tool, I had a second tool. I tried to make it a generic build, so I used a % sign to indicate something or other in here. And then I tried to make 2 different builds, like debug and release, which is a second % sign. But make doesn't do that, it doesn't allow it. So I went out to fix make. So I made Bob, because it's a build tool. And Bob works well. It does this by replacing it with regular expressions. Q, XKCD. And that leads to, well, it leads to 2 problems that you expect. On one hand, you now have regular expressions, which means that you can insert arbitrary complexity and make the tool arbitrarily slow, which is terrible. But worse than that, I had it working, and then I found out that the problem I fixed wasn't the problem that needed fixing in make. because I can now indicate arbitrarily complex builds. I can vary on 3 different things at the same time, but I can't actually indicate any dependencies, which is what make is really bad at. So, oh, too bad. Let's take that, put it on the side. It's not a project anymore. Let's go to the next project. So these tools have a problem that they don't have a solution for dependencies. And typical projects, as soon as they start growing, they will have dependencies. They will have transitive dependencies. They will have indirect 5-level deep dependencies. They have external dependencies. So this kind of build system isn't ideal. And of course, there's the historical limitations of make. That's sort of, you can make do. So the third category, and this is what most people use nowadays. It's a declarative build system. It's like CMake, it's like Meson, it's like many other. They're about as verbose as a build script is. When I'm adding a library, I have to add the library. If I'm adding a dependency, I type it in a build file. If I'm adding an include path, I put it in a build file. If I'm changing a name, I put it in a build file. Any and everything I wanted to do, I have to manually explicitly specify. And this is okay, because it's at least a powerful kind of build system like make. But who has seen a build script? So raise of hands for anybody that has special cases for some targets. That's pretty much half the room. Custom hacks. That's even more. Something like to do, remove this in 5 years. Or just a temporary hack from 2005. But worse, who is for sure that you don't have this? That's 2. Remember that you can override add library. And you can do really ugly things there. And anybody can do that in somebody else's script that you happen to include, maybe through find package. So it's really, really hard to have a build system that actually is sane and well-defined. So let's go to prescriptive and generative build systems. Instead of writing down what I'm building, I'm writing down how to figure out what to build. And then I tell it to go figure out what's there to build. This is close to a functional one, but this is taking, instead of the custom rule set, it's taking the, let's read your code and figure out how a developer would figure out what to build, and then do that. And one thing that's special is that you shouldn't allow a whole lot of room for adjustments and exceptions. By the time you do that, you'll basically be just overriding everything, and people will use that as much as they can. So the best thing you learn is that nobody else is doing this either. So in such a build system, nobody is doing the override kind of thing that you can do. Sounds obvious, but it's a good thing. The downside is that you get a complicated build tool. It reads your code. It has to read your code, otherwise it doesn't know what to build. So I have a build tool that's reading all my code at basically build time, going through 250 megabytes of code, figuring out what to do with it, solving all sorts of, probably not NP-complete problems, but fairly hard problems, just to get something to build. This is not like make or a shell script. This is way more complicated. And moreover, you need to fit to what the tool wants. If the tool wants to have CMake files for finding out where a root is, or some kind of project layout, if you don't do that, it just doesn't work. So let's go about breaking the cycle of complexity. I'm not happy with complexity. So instead of doing this, we should target beginners. We should make the tool as simple as can be. We should have very little configuration. When I'm building Hello World, I know what to build. There's a Hello World. It needs no configuration, especially if it's for my own target, as far as reasonably possible. But if you do want configurability, just have some tiny things like making a different type. Maybe it should be a shared library and not a static one. Maybe it should be a different name. And maybe I want to build this library as an executable for some odd reason, or vice versa. So we're limiting creativity. And like Meson also does, I learned this week, we make it not Turing complete. And that's an explicit goal. Turing completeness basically means that you can make it do any arbitrary complexity. And that can be good. You've seen the talk by, what's his name? The mathematical guy. And he basically has a Turing complete language because he's targeting smart people that are going to be basically hurting themselves if they use it too much. And that allows them to have infinite freedom and creativity in what they make. And they use the node graph, for example, to make a top-down shooter. Well, that's your own problem, but that's what you get with string completeness. In a build system that people are going to be using that's not you want to prevent people from doing that kind of thing, so you have a build system you can understand and mostly ignore. So we make clear what the tool does and what it doesn't. We make sure we don't have a whole lot of deployment types. We don't upload to a target. We don't upload to a build server. We build. It's a build tool. We have an error if you have something that would be breaking the build. Something that many people do in a build system is have a target that compiles to a file, and then have that file be updated in a second rule to the same file. That works in make, but it shouldn't. Because if I see the file with a certain timestamp, is it before or after that operation? No idea. There's no way to find out, which means your build is not reproducible, it's not reliable. And in some cases, you can have situations that you know ahead of time there's going to be something that will be breaking the build if you keep this up, such as having two headers with the same name in different components. And an include that points to one of them, but not definitely to one of them. Maybe both, maybe one. Just keep your fingers crossed it's going to find the right one. And if somebody changes the dependency, it's going to fall over. So the fix is to make it prescriptive and to make a generative build system. And this is a terrible idea, because prescriptive systems always fail. And they fail because people don't like changing habits. They don't like being prescribed things. They like to have their own freedom, their own creativity. They want to do what they want. Let's just look at the examples from the common world. People smoke, people gamble. It's a bad thing. They choose to do it, and they have the freedom to do it. But then why does it work for Java? Why does it work for BASIC? It's not this basic, but the more advanced ones. Why does it work for Pascal and Delphi and C#? If this works for everybody else, why doesn't it work for us? Why are we in such a terrible, complicated situation? And that's because we have an inheritance. We got C's environment, and C started before we had good build systems, before we had computers that could run good build systems. Because we have 4 kilobytes of RAM, you're not going to load a big build system in that because there's no space. You're not even going to load your source file. It doesn't fit. And C didn't standardize one, of course, because they didn't exist. And people forked and innovated whatever they could after that, which means we have a zoo of tools and inscrutable build solutions. We don't have a good solution. We have a whole ton of bad solutions. And C++ said, yeah, sure, we'll do that. So let's find out why we can make a prescriptive solution work. Because we can, but we have to make sure that we don't accidentally trigger the things that make people hate it. So what about, we don't prescribe something new. We just take what's there, figure out what the status quo is, and prescribe that. So we tell you to do what you're already doing in a structured way, so that we know what's actually there. We can explain it to everybody else. We make sure that everything in there is such that we can derive things from the code. So if you have a current way of working that doesn't allow this, we are going to have to push you a little bit, but we prefer not to. We allow the user to override when necessary. So we take a standardized project layout. So we have a component, we have source, include, test, document, examples, third party, external. I could explain this, but I'm choosing not to, because somebody else did way better. And they made this. That's a pitchfork. And this is about the pitchfork proposal by Colby Pike, where he basically takes what's currently the de facto standard and codifies it, and says this is what the build system should be, this is what the project layout should be, and if you follow this, then we get advantages. So if I'm making a tool and somebody has followed this pitchfork proposal, I can warn you. You are including a include/detail file from somebody else, therefore you're doing something that's not right, before it actually breaks. I could get the implicit at-home feeling. I'm in a new code base. I find a whole bunch of components. I don't know the components, but I know they're components. I know that this is a source. I know this is the public includes. I can figure out what's where just by looking at it. And I can get all my dependencies by just looking at the code, because my code is sane. So what exactly are dependencies? So the short intro, we have compile time, link time, and runtime dependencies. We have compile time dependencies. They are the typical includes. Pretty soon there will be imports. There will be export imports. And that's about as much as you can get. You have link time dependencies. Somebody has an extern double. This is not a compile time dependency because you don't need to include the header file to get it, but you have to be there at link time, otherwise it doesn't link. You can have a function declaration. You can do that in your own files. You don't need to include the files, but if you don't include it, it's just a link time dependency, which means that you may have the wrong prototype and it's just going to fail at link time, or worse, at runtime. And then there's runtime dependencies. We have shared libraries, we have plugins, we have a database that needs to be running, we have an internet that you need to be able to reach to have something work. You have the same operating system function, you have a native system call that you're calling. There are thousands of things you can have as a runtime dependency. As a general guideline, I like compile time dependencies. And I like them way more than link time, because if I can break my build, and if I can look at the code and know what's going on, that is good. And I like link time dependencies better than runtime dependencies, because if I can figure out that my build is broken before I ship it to the customer, that makes me quite happy. So you can take those dependencies and specify them manually. There's CMake, there's target link libraries. You can indicate how you want the dependencies to be there. But people will work around this by having an absolute or relative include. You know, the dot slash something or other include. They will include from the project root. They will include from the home root of your computer. It's terrible, but somebody does. And worst of all, they will be overspecified and underspecified at the same time. You have a series of components. Somebody adds links between them. You include some files. At some point, you're removing the include. But nobody notices that you could now remove the link from the build file. So it's just there. At some point, somebody takes one of the bottom end components, and because it doesn't actually use one of the other ones, you just add a link. And now there's a cycle. When there isn't actually a cycle even. So we have an overspecified link and an underspecified link, and that's causing your build to fail. And because you have this, it's hard to fix. I have underspecified links, which means that if I remove some of the overspecified ones, the build is going to break. Because somebody's relying on your overspecified dependency by being underspecified. So the worse this gets, and the bigger your project is, the harder it gets to ever come out of it. And before you know it, you're at this point. And this is a tiny project. I picked this because if I put it on a slide, you can at least see components. I had a different one. It had about 2,600 nodes. That's no point. It's just a blur. So the root problem behind this, it's not that we don't want to, but we're human. We are going to be looking at the code. We're going to figure out what to do. We add includes, we remove includes. If it doesn't compile, okay, we'll add something. If it does compile, I'm not going to remove it. I'm not going to add anything else that might need to be there. And this is because humans are smart. We do the smart work. We do the actual implementation. But we're fallible. We are really bad at doing things consistently. We have an error rate. And the error rate is, I guess, 2%. It's probably more, depending on who you talk to. Computers, on the other hand, are really, really, really consistent. And they're really consistently dumb. Which means that they can do something, but they cannot think about it. So they have to explain something really well. But if you do, they are very, very, very consistent. And they'll have an error rate of less than 1 in 10 to the 12th. Which, written out as a percentage, looks like this. It's really low. And the fundamental bit that you get to is that you shouldn't repeat yourself. When I put something in my code, I have an include. And this makes a dependency to a library. If I put that same logic and the same knowledge in the build file, I am repeating myself. And there are two common things to say, which is dry and wet, where dry is don't repeat yourself, and wet is write everything twice, thrice, 30 times, however often you want. And the best thing is to make sure you don't repeat yourself. So don't repeat yourself. So I don't want to put things in a build file. And if I'm not hard-coding my inferred data, it cannot be out of date. I can't forget to update a file that I don't have. So we set out to make a tool, CPP dependencies. And the basic idea is I take your code, all of it, including third-party dependencies, including any include files. I just take the entire thing, I read all of it into some internal structure. I figure out what things you're including and importing. Given these things, I know which files include what other files. That gives me a tree. I can discover your transitive dependencies. I figure out I have a component A using component B, and in its header, I'm using component C, so that's a public transitive include. I can have private transitive includes. We know which of your header files are not being included. Maybe you just have a whole bunch of code that nobody's ever using. We know what include paths we need. Somebody's including your file with one path, somebody's including it with a second path. We can basically get everything out. We have component-wise thinking. So the Pitchfork proposals gives us component roots. We can also have some other way of figuring out what the component root is. We can guess. It's a terrible idea. I've tried it a few times, it never works. But if we find out the component roots, we know all the files. We know your public and your private dependencies. We know your public and private include paths. This is what your CMake file has. It's 95%. It's not everything. But if you have this 95% and you can automate that, that means you're just modifying the 5% that needs somebody with intelligence, with skill to look at it. So we started to use it on our code base. We have about 7 million lines of code, 500 components, a whole ton of test coverage, and that's good. And I've tested it on a 2012 4-core laptop with a whole ton of memory, because I'm reading all the code. And the expectancy is I should be able to at least sort of match the C preprocessor. If I can't do that, that's just slow. It's unusable. So we can run it on that code base within about 2 seconds if I have a hot cache. I'm limited by my operating system and my SSD if I'm with a cold cache. So you can try to optimize it, but it doesn't even help anymore. And this is fast enough. I can run this with interactive analysis. I can just go send it a command. I can find out short of paths between things. And the commands are fast enough to do interactive analysis and looking at components. I can detect cycles. I can put it in the build system, not slow down the build, and have it break the build if somebody makes a cycle. I can generate my CMake list. So I don't write my CMake list anymore. I haven't written one in about 2 years. And I'm still using CMake in that. And the last time I checked in the full code base, we do about 60% auto-generated. We have small additions because some people really like short names and code bases have big names, so And we talked about it. I've given a talk at Meeting C++ in 2016 and 17 about this tool. So how to make this into a build system? Because if I'm looking at this from a simplicity point of view, I have a shell script, it runs the dependency checker, it goes run CMake, it needs Ninja, all of those tools can fail, there's a whole lot of complexity hidden behind it. And in the end, it already has all the information. It doesn't know some things, it has all the things it needs to know. So just build. So I forked it, and I made a tool called Evoke. This is the simple solution to the build system problem. I've looked at Evoke on Merriam-Webster. It's basically calling forth something, making something into existence, recreating it imaginatively. That's basically what a build tool does. It looks at your code imaginatively and makes a thing. There we go. So you take the dependency checker, CPP dependencies, you take CMake, everything's generated, you take Ninja to build something. Maybe you take a package manager. I'm not 100% sure yet. Because while I like having everything in one tool that does all the things you need to, I don't like having a build that goes out on the internet and goes surfs for a bit, figures out what to do, looks at a few ads, and then downloads a package. That may or may not have been the one you want. It may have changed, or be unreliable, or leftpad. So leftpad was a package that was on the internet, somebody removed it at some point, and caused most of the internet to break. So I want a reliable build, so maybe I don't want a package manager, but I think I do. I'm still undecided. And then we take all those things, roll it into one, make it runnable, make it fast. And then at some point, you make it run continuously. And running a build continuously comes with its own dangers. You could do this right now. You can take the entire toolchain that you have, CPP dependencies, CMake, Ninja. Watch Ninja. There's a command called watch, and it reruns something every 2 seconds. And that makes it so your build runs all the time. It also means that if you're changing a file while it's being compiled, you may end up in a problem. We're also going to be cross-compiling. So we have a race condition in the build. If I have a file, I edit it, and at that point it's being compiled, say we're including some ASIO stuff and it's compiling for 10 seconds, it's a race condition I can make. Now the timestamp on my header file is going to be after the build was started. The timestamp on the object file is going to be after my header file was saved, which means that the build doesn't know that it's out of date. It's not going to trigger a rebuild. It's not even going to try. And you're basically out of luck until you do a clean build. But I was just trying to do a continuous build. That's the whole reason I don't want this. I want to do a continuous build. So you can fix this in the tool by backdating your output to when you started, or by using hashing. That requires way more changes. It requires operating system changes, file system changes. So think 2040 for that. So that's not going to happen. There's a second one that's wrong with build systems, and that's we hide warnings. So who here uses W error? Why do you use W error?
For this.
Yeah. So the problem with warnings is that when I have a warning, I build, I get a warning. I do an incremental rebuild, I don't have a warning. I change a file, I get the warning again. I do a rebuild, I lose it again. I'm doing a continuous build, I see a warning, and it's gone. So the only reason to have W error on is so that the warning is an error. I keep it on screen. I keep having the warning. I can actually fix it. So how about instead of using W error, which is very popular, we just cache the warnings and re-emit them when they're not being rebuilt. It can break some corner cases, but you don't want them anyway, because if you have those in your build, it's not reproducible. So we take the basic design, take all the includes and imports, derive the file level dependencies, ask a package manager. I've found all these files, and I have these 3 includes. I don't know what they are. Maybe you can tell me. Then it goes and finds what to do with it. Say I'm including catch.hpp, it's going to find catch, Phil Nash's library. It's going to download it, put it somewhere, find dependencies, download them. I'm going to reread the entire tree to figure out what to build. Then I take all that, translate it to component level dependencies, take all of that, make it into file level commands, make the file level commands run. We can do that. There are some limitations, and those are the current limitations. It derives the dependencies from includes and imports, and you can do really, really ugly stuff with them. You can use macros. You can include file, as in yourself. And if you do that, it's not going to recognize it. It's just going to read over it and ignore it. You can have includes that are ambiguous. It's horrible for your build, but if it finds it, it's not going to pick for you. It's just going to say, hey, there's this include. It's in 2 places. I don't know which one you want, so go and make it unique. And then there's the 5% of stuff that you might want to put in a build system, probably shouldn't, and that you just can't do here. So you cannot go and publish a file, you cannot upload it to your target directly, you just can't do it. And there's the if-def problem, which is probably going to give you most of the bad results. It doesn't know what your X is. So it doesn't know which of those 2 files it's going to include. So the best guess I can do is just pretend that they're both there, and if I can't find one, probably not needed. This is nearly always just the Windows and an macOS or a Linux file. So most of the time, this isn't a problem. There's toolchain switching. It would be nice if I could use Clang, and currently it does GCC. There's a command line argument. It's not quite there yet. It's not implemented far enough. And there's a module support, because the entire modules reading all your code maps very nicely to reading all your code. So it's implemented as per current TS, and the current Clang builds match that design. I haven't gotten around to testing that. I really need to. I need to find somebody who's made an implementation with modules so I can test that. And it doesn't include the changes that somebody made earlier this week. I'm not that fast. It doesn't have Android tested. I have Android in there, so you should be able to take your code, say target is Android, get an APK file, shove it on the system and run, because it's simple. That's untested. And there's a whole lot of unimplemented. There's no OS X, there's no Windows, there's no iOS. They can be in there, I just haven't yet. This work. And there's a package manager link. I'm still not entirely sure if it should be there. But it's not implemented properly. I still need to do the package config link. I need to go to VC package to get some information. I need to get it out. I have tested it, and it works. Tested it with a self-written package system, but that is miles from release quality. So for the talk, I've just taken it, commented it out. I'm not doing that now, especially with an internet connection. I am very open to contributors. Come talk to me after the talk if you're interested. Reach out, and especially if you can't code, because that's the whole target of it. Please come talk to me. So let's have a demo, if we have time. And it looks like we have time. Are you okay? Okay. We are seeing the same thing? We are seeing the same thing. That's good. I have an empty file, an empty folder. Let's first do the hello world. I don't have anything typed here yet. I'm just empty folder. Let's make a source folder for an executable called hello. Oh. Let's pretend we're not the VI using people. We're a beginner. This text is going to be a little bit small. I might show it on the console later, but I'm basically just typing the standard hello world. Don't use endline. You don't use endline. Okay. If you wonder why that's bad, talk to Jason Turner. Or anybody here, probably. So let's build. Done. There we go. That's hello world. I'm not going to drop this mic. It's going to be hairy. Also, I've heard that it's really bad for the equipment. So, but why would we stop here? I mean, we've got hello world. We can generalize this. Let's make a library out of it. Yep. So let's have a header called greeting. And we are going to be using string because we're not C programmers. That's going to be good then. So we have a header. We can make an implementation. I'll check that in a second. So let's have a good default language. So there we go. You have a greeting. And let's check if what you said was correct. It's singular.
My bad.
And let's use the library. And build. We have a bug. So let's fix that. Any preference for language?
Dutch.
Good job. Dutch. We're done. We have a library, we have an interface. It works. It's Dutch. But of course, this is just making code. And we shouldn't be teaching people to make code. You should be unit testing your stuff. What's up? What's wrong with you? Why are we not unit testing? I would have tried to do this live, but I'm a bit nervous about the rest I've done so far. So I did prepare this one. And I need to put it in the right folder. And the tests are good.
How did it find catch? Sorry.
So this is where I'm cheating. Catch is a globally installed one. Let's go for a second demo, because this is a simple project. I mean, we have just 2 components. We can do more complicated stuff with a bunch of examples. And that's all the examples built. Any preference?
Conway.
Conway. So we can do graphics, we can do complicated things. This is a different library that I will be demoing at CPP on C, assuming I got accepted. But building this is no harder. This is just graphics, we use a library, we do everything. And if we want to know what's up, we can still use CP dependencies. We get dependencies in dot format. We can use graphviz. To make that into a graphic, we can use the GIMP to look at it. And this shows we have 5 examples that all depend on a library. Now, I don't have a demo that uses transitive dependencies for this, but it will handle them just fine. Let's see how fast we can get to all the slides. Yeah, there's a faster way. Yeah, we're at 100-ish. So we had a hello world from scratch with a library, with a unit test. It took 7 minutes to code it from scratch and showcase Pixel. So I want to ask you to help me make C++ a simpler place. Thank you.